I will present you some work related to how AI can revisit some data assimilation methods to produce SST near real-time products. So regarding the outline of the presentation, it won't be too technical, except in the middle maybe, but mostly I will focus on some use case related to the SST products on the Baltic Sea we already talked a bit about earlier, and that is delivered to Copernicus Marine Service. It's not working. Maybe with this one, that's okay. Yeah. Not working either. Maybe I have to. It's space. Yeah. Okay. Thanks. Okay, so from a very broad point of view, I guess we are all dealing in our communities with these different blocks based on physical knowledge, observations that we aim at combining through data assimilation schemes. So typically what you want to do is to combine your physical knowledge with some satellite observation, for instance, in our case for the SST, so that you're able in the end to produce some sort of non-gappy L4 products to retrieve the full SST state. And as you probably know, over the last few years, artificial intelligence changed a bit, let's say, the way we conceive the solution of the data assimilation problem with different approaches. On the left, you have the hybrid approaches, where typically you will keep the same system, the same operational pipeline than before, but you will inject some AI blocks, either in the physical knowledge, in the observations retrieval, or in the assimilation scheme. And you can also go to what is called end-to-end approaches on the right. So typically you replace your full data assimilation scheme with some sort of AI architectures to go directly from the observations to the reconstruction of the state. So I won't be too technical, just a few notations to follow what I'm going to say in the following of the presentation. What we want to do here is to retrieve the SST based on the observations that I called X, which is the state space. And we typically want to reconstruct this SST field based on gappy and potentially noisy observations that I denote here as Y. And whatever the communities you're part of, when you want to build these L4 products, most of the time, in the background, you will rely on some of compromise between the observations and the prior knowledge that is denoted as phi here, and you want to minimize a cost function to do that, which involves some mathematical operations related typically to some sort of gradient step iteration when you start from the initial condition, then you want to find the optimal state of your system, again, as a compromise between the observations and your physical knowledge. But there is a few problems here. First, the model is generally quite computationally expensive to run. The numerical methods to run the gradient step descent is also very computationally expensive to run. Plus, you have some limitations that have been discussed before related to the physics encoded in the model. So how AI can help us to go beyond that? Typically, we want to build purely data-driven methods. So starting from observations, you want to reconstruct your space, your SST fields. So here, what I'm doing, because the model is too expensive, I replace the model by some sort of AI blocks itself. And as I said before, the numerical methods to reach the optimal state is itself very expensive. So again, I want to add a second AI component to speed up the optimization of the process, which means that in the end, I keep the exact same assimilation schemes than before, just optimizing some parameters that are predefined before. And I will do that by jointly train the physical knowledge, the operator phi, and the numerical methods to solve for the problem. And getting back to a very basic deep learning concept, you have a database with inputs and targets, and you want to build some sort of blue blocks, which is an AI blocks. When filling it with specific inputs, typically L3 observations, you want as outputs to get as close as possible as the reality. And getting back to what I presented before, the blue block here is nothing else than the assimilation scheme that you, or some of you, used to apply on your day-to-day operational scheme. And if I transpose this basic deep learning concepts to our problem of assimilation, we get back to these figures with blue and red blocks that are interacting together, where you want to fine-tune, optimize the assimilation scheme, again, to find compromise between observations and some prior knowledge so that you get as close as possible as a true SST reconstruction. So I'm done with the technical part. Let's see how it works in terms of operations. So I will work on some use case here. So as I said before, it's a Baltic SST near real-time products delivered by DMI, which runs an optimal interpolation schemes. And we built some sort of experiment in which we kept the SLSTR satellite observation for validation and used the other satellites available in the L3 product to build the near real-time reconstruction. We target a quite high resolution at 0.02 degree over the entire North Baltic Sea, which can raise some issues for AI methods because it can be quite huge considering a specific assimilation window. So what we did, we split the problems into two terms, a coarse approximation of the SST field at 0.2 degree, followed by an estimation of the anomaly between the coarse reconstruction of the SST and the anomaly between this coarse resolution and the high resolution observation, which enables to split the domain into smaller patches, which corresponds basically to the space-time correlation of this anomaly, which solves the problem of the memory computational issues. So this is from the technical part to the operation of the method. And what about the results if we compare the outputs of the DMI optimal interpolation scheme with this AI reinterpretation of the L4 product? So typically here you see on the year 2021 that we use for validation, some pixel-wise temporally aggregated RMSE in terms of relative gain. And so typically the blue, the better for the AI methods. And you can see that overall on this 2021, we perform better. There is still some red areas, but it is quite promising to turn this family of methods into operations. Same thing here with spatial RMSE. So typically we plot a weekly box plot of this spatial RMSE over the year 2021. And you can see on the top panel, so the orange box plots that we again perform better than the DMI OI scheme. And on the specific interior Baltic Sea subdomain in the bottom panel, again, we mostly outperform the scheme, even if we have some variability during winter seasons. And visually speaking, does this kind of methods really improved the outputs of the OI scheme? So on the top panel, you have the assimilation window we use with the L3 product as inputs of the neural networks. And on the bottom, you have a comparison between the DMI OI and the algorithm that we developed that is called 4D VARNet. And you can see from there some retrieval on finer scale processes that you don't have in the DMI OI scheme. Maybe a bit more explicitly on this figure. On the right, you have on a specific day some gradient field of the SST for the OI scheme. And on the right, the same gradient SST field computed based on the AI method retrieval, where you can see that you're able to retrieve these fine-scale processes contained in the observations that you tend to smooth out a little bit with traditional data assimilation methods. This is confirmed by a spectral analysis on this year. So we also developed with TLS in France an algorithm to adapt what is done in sea surface height based on altimeter data for SST by computing lines randomly across the entire domain to compute spectral metrics without having to interpolate where you have land, for instance. And what you can see on the right panel is that basically the dashed lines that are the outcomes of the AI methods generally outperforms the actual resolutions retrieved by the optimal interpolation methods, whatever the subdomain considered. And to finish the presentation, just a few words about the extension of this kind of scheme. For now, this is deterministic, meaning that you have some inputs and the models give you some outputs. What is sometimes nice with all these new AI methods is that it's quite plug and play. And instead of training your model with deterministic loss, you can use some sort of probabilistic loss, which means that if you manage to do that, you will be able to generate members for your reconstruction and not only one single output. And if you have members, you have access to uncertainty quantification. This is exactly what we did in this scheme. So just the same panels than before. I'm not diving into the technique, but I replaced the pi operator, which was a neural network, a deterministic one before, by some sort of what we call generative AI models, for those who heard about this term, which enables to generate members in the distribution and computing specific metrics to validate like CRPS, the lower the better. You can see that you're able, again, to outperform the uncertainty quantification compared to using standard deviations computed by optimal interpolation and traditional data assimilation scheme. And final slide, what are the potential extensions? This was for near real-time product. Again, this is quite plug and play. So you can go to forecasting with this class of methods. You can go to multivariate estimation, for instance, by combining different sources of data, not only SST, but SSS, SSH, based on different sensors, which can obviously help for the estimation of the SST. And take-home messages, the aim of this work, and in which it's successful, it was able to bridge traditional data assimilation scheme with AI. And yeah, it's considerably easing the use of multimodal observations compared to what we do in traditional data assimilation scheme, with many potential extension, as I mentioned, compared to related to multimodal estimation and also probabilistic extension. Thanks for your attention. And if you have questions, I'm glad to answer.
Thank you. And now it's time for question and then for discussion on Greece priorities.
Vasily, you had a question, I think.
The microphone for the questions. So
you can just come here. Yeah.
Yeah, thank you for
hi.
Thank you for the nice presentation. My question is that the state vector that you use in both the cases, in the optimal interpolation as well as in your neural network case, are the same? Means you take the same variables or only just the SST?
Yeah, it just relies as inputs as the L3 observations for the SST, for both the optimal interpolation scheme and the neural networks.
So the state variable is only the sea surface temperature?
Yeah.
So have you seen the impact on the other parameters after assimilation?
No, we didn't try to use that in some sort of broader assimilation scheme as the one Vasily presented earlier, for instance. But of course, it would be a next step question is it a really good way to use this kind of product in a data assimilation scheme for a more complex model, or do you want to use directly AI to do the same, which is an open question.
Okay. So normally, like if we use optimal interpolation kind of a technique, what we see is that even the assimilation of SST alone will tend to improve your mixed layer depth as well as the currents to some extent. So whether the skill of the AI assimilation scheme would outperform the optimal interpolation scheme, that is the question.
Yeah, this has to be tested definitely to go to not only maybe multivariate, but also to include the depth and how it impacts the temperature. Yeah, thanks. Vasily, yeah.
My question is, the model errors are usually spatially varied.
Yeah.
So when you train in this small box that you randomly shift over the entire domain, you expect that the model will generalize over
yes,
the
definitely.
domain.
Yeah.
Does it mean that you essentially have the errors spatially uniform?
I won't say uniform. I say it will rely on the exact same scheme that is stationary, but it does not mean that the error is the same on the entire domain. It's just the same model that
but your weights will be the same.
Sorry?
But your weights will be the same.
Yeah, the weight will.
Where you shift.
Yeah. You're right. But this is also, it's diving a bit more further into the extension of this model. You can probably complexify the model to account for some specific spatial behaviors. And in a way, it's done by using additional features in the model, like topography or some background covariances that you used to have in the OI scheme. You can fit that in your neural network so that, of course, it's the same weight, but it adapts to some specific features. So same model, but different outputs.
Thanks.
Other question there?
I'm sorry if I missed it, but you mentioned that you withheld the SLSTR data, and I didn't quite catch the validation bit of that.
This one maybe, for instance, or you say that I removed the SLSTR, I keep the data for validation, yeah?
So that is with respect, that's improved RMS.
Yeah, this is computed based on SLSTR. Yeah,
okay.
You compare the difference between the optimal interpolation scheme and SLSTR, the same with the AI methods, and you compare the gain, the relative gain. And you can do that because even if you remove the SLSTR, you're using this coarse approximation of the state by aggregating all the information in the data assimilation window here. But you don't do it by yourself. You let the network learn by itself what is the coarse resolution based on this spacetime window. Even if you don't have SLSTR, it managed to do that. And of course, we expect the performance to be better if we keep SLSTR for true operations product.
More question? I think this was the last question. Maybe it's time to go to the discussion about the GHRSST priorities. Please. There are no priorities. What about it fluxes, for instance? We were discussing in the previous talk about effect of temperature over CIs and impact of very strong difference between higher CIs. We are, I suppose, fluxes are computed using bulk formula that are being produced for very different conditions respect to the ice CIs. I don't know if this can be considered in the future development of this particular problem. Last question about priority and before to leave, because if there are no priority, it's a matter of fact. Do you think that it's time to move to the neural network artificial intelligence for reconstruction of field under cloud cover or not? Can stay with the optical interpolation or for the VAR? No, I think definitely not. Okay. I don't want to insist too much if there's no way to stimulate people. Even Peter may make no question. So this means that we are at the end of the discussion.
I think
I think we can
we
close
can
here.
let things sink in over the next few days. And if there are any points to be brought up, we still have the reporting session on Friday where, if something comes to mind, you can bring it up there. And then we also have the Padlet where the QR code is on these poster boards there. So throughout the week, you can also add any inputs or feedback that you have about GRIS priorities for all the sessions, for anything else. So do that. And then,
Okay, let me close this session. Thank you very much to the presenters. Very interesting section. So.
And for those who are going to take part in the advisory council meeting, we're doing it here in this room, and I think we start at 6:30. So those who are not taking part in the advisory council meeting, you can go home or like go explore the city, and yeah.